Okay, let's get started. All right. So good morning, everyone. I'm Kijin Song, and I'm a postdoc researcher in the Urban Information Lab at the School of Architecture at UT Austin. So welcome to our lightning talk series on smart city research. This talk series is funded through the UT's Good System project. So we invite speakers from academia, industry, and communities to share the research events and the needs related to the smart cities. So if you are interested in this topic, please feel free to visit our website to see our past talk and other activities at smartcity.tech.utexas.edu. Today, we are very excited to have Dr. Carolina Osorio as our guest speaker. Dr. Carolina Osorio is a staff research scientist at Google Research. She is also a faculty at HEC Montreal, where she holds the Scale AI Research Chair in Artificial Intelligence for Urban Mobility and Logistics. Dr. Osorio has consulted for Alphabet Sidewalk Labs and has collaborated with top private and public sectors, transportation and supply chain stakeholders, including Zipcar, Ford Motor Company, and New York City Department of Transportation, and the San Diego Association of Governments. Her work focuses on the design of AI and simulation-based optimization algorithms to tackle high-dimensional optimization problems. Dr. Osorio also was recognized as an outstanding early career engineer in the US by the National Academy of Engineering's EU-US Frontiers of Engineering Symposium, and is the recipient of the MIT Technology Review MTech Columbia TR35 Awards, and was on the Good 100 list of innovators in the category of minds that are hacking our surroundings for the better. So her talk for today is titled "Making the Most Out of Sparse Data: The Case of Travel Demand Calibration." So without further ado, I'll pass the mic to Dr. Osorio.
Thank you, Kijin. Thank you for this introduction and this invitation. And thanks, Arya, as well, for putting me in contact with Kijin for this great opportunity. So what I want to talk to you all about today, so as Kijin was mentioning, everything I do is transportation and urban transportation related, with a focus of bringing in ideas from different fields, including machine learning and operations research. And what I want to talk about today is some recent work we've done at Google that looks into how can we help cities make better use of the sparse data they have. And so we'll be looking at that in the context of trying to estimate travel demand. So before we go into that, I want to tell you a little bit about what excites us in this, in my research team. And I'll say also, if folks after this talk, if you feel like some of this is very aligned with what you're doing or your interest, we're always looking out for new ways to collaborate and to connect different types of research initiatives. So feel free to reach out to us. So we're excited in the group of thinking about how to develop better models of urban transportation, in particular simulation-based models. We've been focused on looking into very high resolution models that are called microscopic simulators. So you can see a little video of that here, where you have individual vehicles. They can have different types of behavior or even vehicle technologies. And we have mechanistic behavioral models that describe how drivers and vehicles pick what their origin is, what their departure time is, what their destination is, how they drive, how they change lanes, how they route, like many, many, many different travel decisions that they make when they actually travel on these road networks. And we're interested in developing tools that can help practitioners and academics both specify these simulators, so better calibrate them, meaning better define what inputs they should be giving to these calibrate simulators so the simulators replicate actual traffic conditions. And also we're interested in, once they've been calibrated, how to use them to actually inform transportation operations or planning. Okay, so that's what we call simulation-based optimization. So we develop algorithms that go on top of the simulator in a systematic way so that we can either optimize inputs to the simulator, which is calibration, or we can optimize, policies that we want to evaluate with the simulator. In general, what we've been doing is based off of Sumo, which is an open source traffic simulator. We rely on a variety of different types of input data, including for different case studies that we have potential third-party data from cities. And here's an example of like the two types of optimizations we do. There could be policy optimization or operations optimization. Routing is one example, coming up with routing policies. And then the second type of optimization is actually specifying the simulator. So that's optimization algorithms for calibration problems. So that's what I'm going to talk about today. On the right-hand side, this is a map of the Salt Lake City metropolitan area, and we'll have a case study today that is looking at a part of this network. So before we dive into calibration, which is defining input parameters for the simulator, I want to give you all an overview of what we do in the team. So a good chunk of it is, algorithms for calibration. There's some amount of work on how to advance fundamental questions in transportation science. And if we have time towards the end of my talk today, I'll show you one or two neat slides or recent results that we have in that area. In particular, thinking about how to better describe how traffic propagates in space and time. And then we have a variety of more application-oriented research efforts. For example, a lot of work in how do we design better routing policies. Sustainability impact of routing is something we care about. And more general traditional traffic management problems. We've done a good amount of work, for example, in traffic light optimization. Okay, so what I want to talk about today is calibrating the demand inputs of simulators. So what that means is what amount of trips should I be loading onto the simulator to replicate current traffic conditions? And when I load a certain amount of trips, I need to specify what their departure time is, what their origin is, and what their destination is. So this is something called travel demand calibration. It is often formulated as what's called origin destination calibration, which basically means you have like a metropolitan area, you decompose it into discrete, often traffic analysis zones. And each zone can be a potential origin or a potential destination. And for plausible pairs of origins and destinations, what this problem does is said, what would be the demand, the number of trips that want to go from a given origin to a given destination? So here on the right, there's a simple network. We can have origins 0 and 1 and destination 2. So there would be two possible origin destinations, right? You can go from 0 to 2 or from 1 to 2. And it's a tricky problem to solve. It's often very high dimensional. It's also tricky because these simulators, because of their high resolution, are also compute intensive. So if you just take a general purpose off-the-shelf algorithm to solve these problems at a metropolitan scale or any realistic network, usually the amount of compute time you need to solve them is really significant. So it's, in practice, we don't yet have really good tools for practitioners to solve these problems efficiently. And the second issue that is a big challenge with this problem, and that's what I'm going to focus on today, is the notion of underdetermination. So if you look at the network on the right, imagine you have a traffic sensor on that red dot that says S for sensor. So let's say you've measured there's, 500 vehicles an hour that are crossing that segment. What you really want to know is how many vehicles are going from 0 to 2 and how many are going from 1 to 2. And if all you know is that there's 500 vehicles an hour crossing that sensor, well, there's a large set, often an infinite set of actual demands that would actually lead to 500 vehicles an hour on that sensor, right? You don't really know how many of those 500 are coming from origin 0 or origin 1. And that's what's called an underdetermined problem. It basically lacks identifiability, meaning that with the data that you have, which in this case would be counts at that sensor location, you cannot fully identify what the potential demand is. This is known in practice that this is an issue, but in the usual practice, what they do is they say, well, let's find one demand. that if I load it leads to these 500 vehicles an hour, and now let's do all our analysis based on this demand, right? And that is, if you can imagine, it can lead to really tricky issues, because if you pick the wrong demand, it might be very misleading in terms of the operation and planning insights that you get. So we're very interested in thinking about how can we account for the uncertainty in the demand when we do optimization. And in particular, with the focus of doing robust counterfactual analysis. So when we actually want to solve planning and operational problems, we want to account for the fact that there's a lot of uncertainty in the demand, and it'll give us uncertainty in the recommendations we'll give, but at least it'll be consistent with how much information the data actually gives us. And so we're looking into there's a lot of literature on this problem and how to reduce this level of underdetermination. And often, I think historically, we've been very optimistic in the community, and we've said, well, there's going to be more data and there's going to be higher resolution data. And of course, that helps. But the reality of many cities and municipalities is that they're still working with very sparse data and often low resolution data. And so what we've taken here is a different perspective. And we said, if you have a sparse set of sensors on your network, can you extract more information from those sensors as opposed to buying new sensors or purchasing new types of data? And what is the value of exploiting more information from those sensors? Can you actually reduce the level of underdetermination? So we did, and this is a 6 spatial poster paper. I have the reference at the end of the slides. I'll tell you the big insights we got. We did first some analysis on this thin synthetic network that has 3 origins. So you can go from 0 to 0, 1 to 1, or 2 to 2. And for each OD pair, you have 2 possible routes. And we can show analytically. So assume we have data, vehicle count data on sensor 0 and sensor 1. And what you want to reconstruct is the actual travel demand. So we showed analytically that if you actually just want to match expected counts, so you want to come up with a demand such that the expected counts on this link and on this link match the field data that you have, the problem is still underdetermined. But if you use second order information, in this case, it means if you use covariance information about the counts at S0 and S1, then you actually have a fully determined problem. You can uniquely identify what OD or demand actually led to those counts. So in this simple setting, it's awesome because with just adding, going from first order moment information of the counts to second order, you have full information about the ODs. Now, in a general network, we don't get to, actually totally reduce or eliminate the underdetermination, but we can significantly reduce it. So when we've been working on a larger network, our approach is the following. We've developed a variational inference technique that relies on a couple of building blocks. So it uses this open source simulator that I mentioned, Sumo. It couples it with a simulation platform, Rexim. I put the reference here. It's a really awesome simulation, probabilistic programming simulation tool to actually optimize any form of simulation. It's not tailored just for traffic. So it could be, recommendation systems. It could be simulation of a social network, anything you want. And it uses really neat differentiable variational inference techniques to actually calibrate these simulators. So we've been using that for traffic purposes. And we coupled that with a GAN model, a generative adversarial network formulation, to do a distribution matching approach where we take the sensors in a city and we want to match first order information, so expected counts, and second order information, so covariance information across all these measurements. So what I'll show you now are results initially based on synthetic count data, so simulated data, but it is worth noting that the approach extends to any type of data and any amount of data that you have. It's not a limitation of the approach. So here's our case study with Salt Lake City. We looked at a setting where we have 62 different OD pairs, so 62 possible origin and destinations, and we want to estimate what is the demand across these 62 pairs. The locations of the origins and destinations are here in these green S2 cells. The road network of the model is in the middle, so you can already see a little bit the complexity of the underlying network. And on the right-hand side are actually all the routes that folks can take for every origin destination. And the segments are colored according to how many routes, how many ODs of these 62 have a route that goes through that segment. So the more these colors are towards the blue and the purple, the more the ODs that actually have routes that travel through them are high, which means the higher the underdetermination. So the less, if you have sensors on those segments, the less information you get actually about what the actual travel demand is. So you can see most segments are in their blue and purple, which means that there is a significant amount of underdetermination in this network, which basically means that if you're working with a city that has count data and you want to define the demand, travel demand of that city, there's a lot of uncertainty in terms of what that demand could be. One thing worth noting, our method yields as an output a probability distribution over OD. So you don't get a point estimate, but a full probability distribution. And that is a big part of how we plan to account for uncertainty as we do simulation-based analysis. Okay, so here are some initial results. We use two different benchmarks. SPSA is a commonly used algorithm in a lot of transportation simulation work. It's simultaneous perturbation stochastic approximation. It is a method that is not traffic specific. It is for continuous problems, and it usually doesn't work very well in high dimensional problems like this one. So, caveat. And then we use a different benchmark, which is called a meta model method, which actually is tailored for traffic problems. And for each one of those two benchmarks, we consider two cases, whether or not we regularize the problem. So what we see here, so what do we have here? We have some error statistics on the segment counts. So these are normalized root mean square error. So the smaller the numbers, the better. And if we look at these numbers, so these are initial ODs, like if you just randomly pick an OD, or maybe the city gave you an initial OD that they have from census data, that's what we use to initialize all these methods. You can see that all methods actually reduce the error compared to what we started off with. So we started off with an NRMSE of like 33%. They all reduce it in a statistically significant way. SPSA reduces it only a little bit, and that's expected because it's not, SPSA is meant to actually work either in lower dimensional problems or giving it way more compute time before you terminate it. So, it's kind of expected. But the other benchmark actually does really good compared to our approach, which is adversarial. So in the single digits of NRMSE, which is really great. Now that is measuring performance in terms of, can we replicate the traffic count? But it doesn't tell us anything about, are we getting the correct ODs, which is really what we care about. Are we getting the correct travel demand? So the second part of this table actually speaks to that point. So these are NRMSEs now in terms of the errors between the true ODs, and here, because we're using synthetic data, we know what the true ODs are, and the ODs proposed by these algorithms. So again, you want smaller errors. If you look at actually the SPSA, the errors in the OD space are similar order of magnitude than just the initial points. So it's, again, saying that SPSA is not designed to be terminated within a small computational budget when you're working with high dimensional problems. The second benchmark, it's really interesting what happens to it. So if you look at the median error, there's actually, and you regularize, you can end up with an error of 46%, which is actually really good. But if you then look at the mean, you end up in the 111%, which is very similar actually to the initial point. So that's very, very bad. And I'll explain in a second why that is. And then the proposed approach, it has actually a more systematic error, regardless of whether you look at the mean or the median, which is of the order of 70%, which is considered, given the current setup, considered pretty good. So what is actually happening between these methods? Let me give you a graphical insight. We have on the left, so we ran the second best approach, this meta model approach with regularization. We ran it 100 times. And it gave us 100 solutions. This method actually gives you a point estimate. So one OD is a solution. It doesn't give you a distribution. For those 100 ODs, what we computed is the error with the true OD. And this graph tells us for every element of the OD, so there's 62 elements, it's a 62-dimensional vector. For each one of these 62 elements, what is the average error? Those are the red points. And an error bar of what is the standard deviation of that error. So the bigger these error bars, the more variability there is in the solutions that the method proposed. So what you can see here is, for the benchmark method, the red points are relatively close to the zero line, which is good. It means on average, it's getting really good solutions. but the error bars are very high, meaning that there's a, if you run your algorithm once and then run it a second time, the different ODs you get could be very, very different and very different from the ground truth. On the right-hand side is actually our method. Our method, if you run it once, gives you a distribution of ODs. So what we do is we just run it once and then we sample from that distribution to get 100 ODs. What we see here is, although in some cases the average error is higher than this benchmark, the variability around that is actually really small. So it's much more robust to that uncertainty in the count data that we have. And this is a setting where we actually used information, as I mentioned before, first and second order information about the counts. So the bottom line here is we feel that it's very encouraging both in synthetic toy networks and in larger networks like the Salt Lake City case study to exploit more information from the sensors that we have. We don't necessarily need to be advocating for cities to purchase more data or to be deploying more sensors. Even just taking the data that they have and using higher order statistics from them to solve some of these traditional problems can go a long way in reducing the uncertainty in the inputs of these simulators, and hence also in the outputs when you perform any type of operational or planning analysis. Okay, so I'm wrapping up. I do want to do a quick pitch on more transportation science questions that we've been looking into, in case there are folks in the audience that are interested. We really care also within Google Research of advancing a fundamental understanding of what's happening in transportation networks and what are the traffic dynamics. And so we in the team have been looking at developing what are known as fundamental diagrams for urban segments, which is basically an understanding of how congestion builds up on individual roads as a function of demand. And I think I want to point you towards this right plot here. You see different curves. So the x-axis, you can think of it as travel demand on a road. And then the y-axis is the speed. So, the more there's demand, the lower the speeds. And the different colors are different roads that have different traffic light settings. And basically what we've done is carry out an analysis to understand how the settings of traffic lights impact these fundamental diagrams. Said differently, how the settings of traffic lights impacts the spatial propagation of congestion. And so we have some really neat findings there. If anyone's interested, I can point you to the paper there. And part of what we did there was also understand how traffic light settings impact congestion on upstream segments that are near but the signalized intersection, but not necessarily signalized themselves. And we have some interesting both theoretical and practical insights there. So as a summary, we think from these analyses that there's a lot of potential to exploit more information from the sensors that cities often have. We don't necessarily have to be purchasing more information, deploying new sensors. There's a lot we can still do with what we have. And for problems like travel demand calibration that are known to be very underdetermined, meaning there's a lot of uncertainty in the inputs, we think that it's really important to shed more light on how to use higher order statistics from the data to reduce that uncertainty. And it's critical to actually be able to perform more robust counterfactual analysis. Ongoing work is looking into how to measure and exploit within the GAN technique, spatial temporal dependency that we know exists in transportation networks. And we're using some ideas from one of the benchmarks, actually the meta model benchmark, that uses simpler traffic models. We're using some of those ideas to actually come up with variance reduction techniques to improve the numerical performance of the GAN approach. There's plenty of information in our 6 spatial poster paper if anyone is interested. And with that, I will open the floor to any questions. I think I'm okay on time.
Yeah, thank you so much, Dr. Osorio. Yeah, it was really interesting topic, and I will just wait to see if there is any questions from the audience. Anyone have questions?
I had a question.
So thank you for the very interesting talk. Do you mind going back to the first plot you were showing that you have 3 probabilities, and when you are incorporating yes, here. So yeah, sure. When you are adding the covariance between them, you're adding additional information, and then it is fully specified model. But what happens if instead of like 3 probability, you have 10 probability and 2 sensors?
Yeah. So in this setting, to prove that it was fully specified, we made the assumption that The demands are unknown, but the route choice set and the route choice probabilities are not only known, but also not a function of traffic. So there's not like they're exogenous. Yes, so we have, this can be generalized to, okay, so the main insight before I tell you about the generalization is that when you compute the covariance information, what you get is information about route choice information from ODs that are common to both sensors that you're looking at, right? So in this case, if you have covariance between 0 and 1, you're basically getting information about demand from OD1 that goes to 1, right? And so more generally in a general network, when you're looking into covariances, even if you don't necessarily eliminate underdetermination, you will be getting information about route choice probabilities for any OD that shares routes across those settings. So if you assume like this setting where we know the route choice probabilities, you can actually increase arbitrarily the number of routes per OD. That doesn't change the impact of reduction of underdetermination. However, if you say that your route choices are endogenous, like they depend on traffic conditions, then you don't remove the underdetermination, you just reduce it. And then if you want to generalize this to more ODs, it'll still be a function of for where you have sensors, how many ODs contribute to traffic on those sensors. You know, that analysis, we don't have a clear answer of like under what topology, network topology conditions would you be guaranteed to have fully eliminated underdetermination or just reduced it. But in any real network, you will never be fully eliminating it. And the other challenge is if you look at real data, so second order information, you can get a good signal to noise ratio, but as you go higher or higher in the order of the moments you're trying to evaluate, you know, the signal to noise ratio becomes very small. So even if theoretically there's added value, practically it might be really difficult to you know, come up with a method that actually uses that.
Yeah, that totally makes sense. So so probably what happens if you go to, instead of 3 sub demand, you have 5 demands or 10 demands, and still you have only 2 sensors. Can you impose some sort of like a sparsity? Because if you apply some sort of a sparsity and regularization, still it is underdetermined, but it forces some of them to go to 0. Does it help
Exactly.
final
And that's,
solution, or it is going to hurt you?
So that is the practice right now is always to reduce that underdetermination by adding regularization, like, you know, an L1 norm or something like that. We think that it's a good, I mean, practitioners should stick to that, but what we'd like to do, at least if they want to do that, is to compare with and without regularization, what are the types of solutions that you're getting. Because when you actually do a lot of this regularization, the choices are often made based on mathematical criteria of what is a good regularizing function, as opposed to, you know, what does that mean in terms of traffic implications and like actual ODs that I'm generating, right? Because you're biasing at the end of the day that solution. Yeah, but yeah, the regularization is essential because there's just so much underdetermination that you actually have to enforce it at some point to come up with a plausible OD. And the other challenge we've had is that the way regularization is being used is often based on using also information from prior ODs. So historical ODs based on census data maybe was collected, I don't know, 5 years ago, and saying, well, we don't think that the travel patterns have at least spatially changed that much. And my sense is that that's still a really strong assumption, because even when you look at how, in many cases, those ODs were determined, there's a lot of issues there. And so, yes, some of that structure, you want to preserve it, but I think the current ways that the regularization is defined, I would say we're trusting too much those initial inputs. And that's, of course, biasing the outputs we can get.
Thank you.
Hello, Dr. Altario.
Hi.
Hi, my name is Junfeng Jiao. I'm a director of Urban Information Lab, and sorry I was a little late. This is a final time. The student are busy on final, so I need a little apologize for that. But
No worries.
For the wonderful talk. It's really exciting. I will ask 2 questions from a transportation engineering perspective, because that's basically what we do most time. So where the OD size matter the prediction accuracy or have some impact on the you shoot graphics. This is based on the predetermined OD. Will the unit analysis of OD affect the prediction accuracy? The first question. The second question is you mentioned a spatial temporal information to include and better calibrate the prediction results. So we know, as you mentioned, the OD size or OD information with from sensors every 5 years they have an update, or every 10 years, or every 1 year. So that is still very long time. So my second question is, how do you think about include the more timely data, like monthly data? We do have a transportation survey, the behavior surveys. Will that significantly increase the model result? That's the two questions. Thank you.
Awesome. Yeah. So the first question, I think there were two aspects to it. One is, how does this approach scale in higher dimensions? And so far we haven't had issues, but it is an open question because right now we still tackle problems that are not time dependent. So we look at one single OD for, let's say, 5 to 6 p.m. And there is dynamics in terms of, congestion propagating and dissipating within that hour, but we're trying to estimate a single OD distribution. The next step is actually a time-dependent OD distribution that evolves over time. And I think it's an open question once we get there. Numerically, will there be issues that arise that we haven't seen yet in the static setting? So that's a good point, and it's something, we will start looking into. We haven't yet. In terms of the spatial temporal, so yes, I think that the more data you can have, the better. The challenge we've had with more recent, or that exists in the literature with recent travel demand surveys, is the sample, right? You usually have the added value is the recency of it. The inconvenience is you have there's a selection bias there, right? Some sampling distribution that you need to understand, which doesn't happen with census. But yes, my general take is any recent information you can get, it is all helpful. I think the question is more, what type of statistics from those samples could be less biased, or could you know more about the bias to be able to correct for it? And so different types of more recent data might not all contribute in the same way, or you might not all want to use them, for example, to measure flows or to measure travel times. It'll depend on how they were collected. But yeah, and to be honest, the literature, when they talk about underdetermination, they always phrase it as, it's not a big deal because there's more data and there's more recent data and it'll be increasing. And I feel like that's theoretically true, but not practically true, right? If we look at how cities have been collecting data, we've been telling them for decades that, the big data area is here, and now you'll have plenty of data and, all these probe data and, connected vehicles. If we look at how they've changed in the last 5+ years, yes, there's improvements, but we're very far from cities being able to say that the sparsity of the data is not a big issue, right? So I'm less optimistic than I was before. Like, yes, in theory, we will be collecting more data and cities will, be empowered by it. But in practice, I feel like we're still a very long way from there. So I think we should be giving cities more tools to do the best with the sparse data they have, as opposed to like asking them to wait until they get better data.
You've been very nice, called sparse data. I and I probably will call it messy data. The data is super messy.
That's true. There's there's more than just sparsity there. Yeah.
But just the last question: if you change the OD size from a sensor track or like to the smaller size, like a block group, will your prediction result be different? Have you tested that?
That's a really good question. So, okay, so I'll tell you like the technical answer, and I'll tell you a more high level answer. So the technical answer is yes. As the size of your analysis zone decreases, the dimensionality of your problem increases. So it becomes trickier. We have not done an analysis that says, to what extent, how does the quality of the OD change, and how much does because we're actually increasing the dimensionality of the problem, we're also increasing the level of underdetermination. So, what's the trade-off? It could be interesting, but my take on this is a little different. So historically, the reason we use TASs is from a planning perspective, right? Like that's the analysis unit that cities and municipalities work with. And if we can give them a solution in that space, that's great. But because we decompose the space, the city discretely, that's what leads to really difficult optimization problems, right? Because now we're looking at all pairwise combinations of zones, which is where, the dimensionality explodes. Now, I actually think that we should be advocating to work in a continuous space, we don't discretize space anymore. We say, I have continuous space and I want to find travel demand, a distribution of travel demand in this continuous space. That there's pros and cons. The pro is from an algorithmic perspective, it's a much easier problem to solve. It would significantly reduce underdetermination by definition, because now we're not looking at pairwise combinations, but we have you could have a parametric distribution with a handful of parameters that defines the entire OD over space. The disadvantage is it really goes against the culture of what cities do, right? Because historically, traditionally, everything has been based on TASes. If you give them now a solution that, yes, you could tell them, you can map it back to your TASes, but it's not defined based on the TASes. I think there could be some pushback in practice to adopting it, but I think that's the way to go, especially because of the level of underdetermination. I don't think we should be working in these discrete spaces. It just makes things worse.
I completely agree with you. We should moderate it in a continuous space and aggregate up to the test level, not going the other way around. Good point.
Agreed.
All right. It was interesting discussion. So yeah, I think, it's already at the time to wrap up. So I want to stop here. If you have any more questions, then feel free to reach out to Dr. Osorio directly. Dr. Osorio, can you please share your email address on the chat?
Yeah, of course. And thanks. I know it's the end of term. It's also the end of term for me. So thanks everyone for making the time. I know it was, you all have really crazy agendas the next few weeks. So thank you.
Thank you. And
Sure. Can you stay for a couple minutes with me and Aya? We want to talk a little more about future possible collaborations.
Yeah, I'm around. I'm available.
Yeah, thank you so much, Dr. Osorio, for your wonderful talk. Yeah, I think, also thank you everyone for joining the talk. And I hope you all have a wonderful weekend. Yeah, bye.
Thank you. Thanks for organizing this.
Mhm.